So this talk is called Surviving Microservices, and you can regard it as a field report. 4 years ago, I set up a Node.js consultancy with a couple of other guys, and we discovered really quickly that if you try to build large applications in JavaScript, it goes badly. JavaScript doesn't, as a language, pretty bad. It doesn't give you much structure. So you need to actually provide that structure yourself. And we tried various different things. And eventually, we run the Node.js meetup in Dublin, in Ireland. We happened to invite Fred George to give us a little talk. And he spoke about programmer anarchy, and he spoke about microservices. And while he was doing that, the light bulbs were going off. Because we suddenly realized that we could apply this architecture to building server-side JavaScript applications, and it will give us a method and a means to control the internal complexity of the application. But it's not a free lunch, of course, because microservices, as you've seen in this conference and the talks, have a whole bunch of challenges themselves. So you've got to adopt a philosophical attitude, which we like to call Kintsugi. So this is a tea bowl, a Japanese tea bowl from the 15th century. And the story goes that at the time, tea ceremonies were all the rage and extremely fashionable and popular. The problem is the tea bowls were made in China because that's where they knew how to make, they knew how to do glazing. So they were very expensive in Japan. The shogun at the time managed to drop his tea bowl and break it. And he was very upset, so he sent it back to China to be fixed. And when the tea bowl came back, it was fixed with ugly metal staples, which offended his aesthetic sense. So he challenged his master craftsman to find a different way of fixing the tea bowl. And what they came up with was Kintsugi, which is to take a gold dust and mix it into a lacquer and then glue it back together again. And the results are actually very beautiful. And this is a philosophical stance that really appeals to me, and it really appeals to the microservices perspective, because it's accepting of breakage and failure. It's accepting that the world that you live in, that things are going to break, and instead of trying to build perfect software, Uwe yesterday was talking about ACID transactions, and he exposed the ugly underbelly of what ACID actually means. If you look closely, you don't actually get the guarantees that you think you're getting. We'll face that fact truthfully up front. Understand actually that your applications are full of failure, and learn to live with it. So, of course, we build a lot of production systems. My company is a consultancy, and we build a whole bunch of different things for people. It's kind of hard to experiment on production systems to understand failure modes. Sure, I mean, you get individual types of failure, and you work around those, and you learn a little bit. But one of the things that we wanted to do was create a test bed, both for the community to experiment with this stuff, but also to run our own experiments. So we have this little system called Nodezoo.com, and if you use Node.js, you'll know that there are now 240,000 modules. Finding the right module, if you want to do LDAP integration, can be kind of hard. So the basic business problem we're trying to solve with this little application, we wanted it to be a real application, was here's a search engine for Node.js modules. And it's a really, really simple application. It talks to Elasticsearch to do the indexing. It queries the npm.js website. It queries GitHub to get stars, all that sort of stuff. So it's a relatively simplistic test bed. It's something that you could build as a monolith, as a mean stack application, quite easily. But we deliberately built it as microservices. And this is the entire application. It's not that many microservices. It's enough that you can get it into your head. There's a web microservice that serves the front end. There's a search microservice that talks to Elasticsearch. There's an info microservice which displays an information page about a module, the number of GitHub stars, etc. There's an update microservice, which listens to update events from NPM. So when I type npm publish and I publish my new module, it'll get that event and put it into my Elasticsearch. And then there's an npm microservice that knows how to talk to npm, and a GitHub microservice that knows how to talk to GitHub. So a system you can get inside your head. The interesting thing about this diagram is this is a simple system, but look at all the arrows, right? Tons of arrows going here, there, and everywhere. You can imagine in a system where you have tens of microservices or hundreds, and you're drawing this diagram to try to show the dependencies and intercommunication, you can't get it inside your head. And this is one of the core criticisms of the microservice architecture is it's not simple. And you would have heard that yesterday in the panel, for example, where one of the points made was there is a lot of friction at the start because you have to try and get this stuff into your head. Yes and no. So we're definitely in the microservices first camp, not the monolith first. And the reason is if you apply the right sort of abstractions to the communication between your microservices, you can make your life a whole lot simpler. So in order to understand the failure modes, you need a little bit of structure. You need a little bit of way to categorize the world. There's synchronous communication, and there's asynchronous over message buses. There's a whole bunch of different ways in which microservices can be structured. Chris Richardson's talk yesterday showed you some of those patterns. So how do you take some of that structure, classify it, and then understand if I have this type of pattern, what type of failures occur? In order to create enough structure to look into the failure modes, I'm going to have to take this application and structure it for you. So that's going to be the next section of the talk, where we kind of look at how the application fits together, and instead of just drawing arrows, we'll try to have some semantic structure to the application. In addition to gaining a lot of experience with Node and microservices, we've come up with a couple of sort of practical approaches that make microservice systems easier to build. One of them is pattern matching. And this means instead of one microservice knowing that another microservice is responsible for something, all that microservice does is emit a message into the world. And other microservices pattern match against that message and decide, this is a message I like, I can work with this message. Fred George spoke about that a little bit, and he builds this in a message bus architecture. But this is an abstraction that gives you an awful lot of flexibility. The other thing that makes your life a lot easier is transport independence. So if you're writing a microservice that is using a HTTP library to make a direct call to another microservice inside that library and knows the URL path and the IP address and the port, you're doing it wrong. That's the path of madness. You'll end up with an extremely complex system. In fact, what you end up with is microservice A is talking to microservice B, and there's a direct dependency, and whenever you update A, you've also got to update B. That's not microservices. That's a distributed monolith, because you just have two pieces of the same service. They happen to be over the network. You need to be able to independently update the pieces for all services. So what does a message look like, since we're so obsessed with messages? Well, it could be XML, it could be JSON, but let's make it JSON. It's easier, and we write Node.js, so it's kind of the obvious thing for us to use. Ultimately, the content of the message is arbitrary. It doesn't really matter what's in there. That's also important because it lets you extend your application over time. But if you look at this message, which is part of this Nodezoo search engine, when I type in a search query, this message gets emitted. And the search microservice that knows how to do searches against Elasticsearch can look for messages that have a role property equal to search and a command property equal to search as well. I'm namespacing a little bit to make my life easier. In another universe, this is a command pattern. Not all microservice interactions have to be command patterns, but this one is fairly analogous. So if I have a whole set of messages and a set of patterns, I effectively have a domain language. I can describe the behavior of my system using messages alone. And if you think about it, this lets you take informal business requirements, translate those into behaviors, and then you can encode the behaviors as messages. And I haven't even spoken about services yet. Now that's a very nice property because it means that you can allocate these messages to services dynamically, or you can change your architecture over time. This is a really nice way to specify microservice systems. And it's one of the reasons, if you take this approach, that microservice first is actually easier than monoliths, because you have to do less design. All you have to do is sit down and think up the messages. And you don't even have to be too worried that you get the right messages. You can always change them later. Let's have a look at the system from the context of this structure. The web microservice, which serves the front end, is going to talk to two other microservices, the search microservice and the info microservice, using two different message patterns. One is role search command search, which we've seen already, and the other is role info command get. So if I want to see the details of the express node module, the number of get stars, that's what does that functionality. And these messages are synchronous request response. I have a user in front of me, I need to get the data, I send a request and it comes back. And if you have a model in your head of a microservice talking to another one via HTTP request, this is it, right? It's synchronous request response. But there are other types of interaction. The ones Fred is particularly keen on. If I look at the update microservice, which gets update events from npm.js, every time somebody does an npm publish, I need to capture that and then send it out into the world. And I might have multiple different kinds of microservices that are interested in that event. And if I want to scale my system, I want to have multiple instances of individual microservices. And in our little model, the npm microservice has its own database where it stores the list of modules that it knows about. I'm not using an external database, I'm using a local database. So it listens for these update messages. And in this case, this is asynchronous. And you can imagine a scenario where you want to scale this up. So you have 10 instances of npm, and you round robin between them. So you get a scalable system. The message doesn't go to all 10, of course. Only one of them takes the message and acts on it. Or you could have a slightly different view, an extension of this approach. And this is analogous to Fred George's model where you're generating insurance quotes or special offers. And in this case, the info page is going to tell you about a node module. Now, a node module has the details from npm, who the maintainers are, details from GitHub, number of stars. And then I might want to extend my system. I might want to look at Travis CI to see is the latest build working, or Twitter to see what the latest tweets are. And I can add microservices to implement that functionality. And the word that I've used there is add, and it's a key word. The reason that microservices are easier than monoliths right from the start is because to create new functionality, you add new microservices. You don't have to change the existing system. You don't have to refactor your data structures. You just add a new service. In this model, the info page, when somebody loads it in their browser, says, OK, everybody has 200 milliseconds to give me some data. If you don't get back to me in 200 milliseconds, that's it. I'm going to just display a blank box. And those messages go out. The npm microservice is listening for it, the GitHub one, maybe the Travis one and the Twitter one if you implement those. They do their processing, whatever that is, and then they emit messages that the info page can listen for itself. This makes you resilient to failure because it doesn't matter if any of these microservices are down, you will still display a page to the user. This is where you get the big win. In a traditional architecture, you'd have to implement this by hand yourself, or you probably wouldn't bother. You just do a sequential set of requests, and you might end up with really, really high latencies if one of these services is slow. In this case, you've said it's much more valuable to the business to display a page, even if all that page says is, sorry, we're loading. as opposed to the user sitting there watching the browser spin. Microservices mean you can do this without writing code. It's just an architectural decision, how you wire the messages together. So if you've been observing the arrow notation closely, you can see that there's actually 4 cases. Messages are either synchronous or asynchronous. So synchronous is a HTTP request. Asynchronous is put it onto Kafka. And then they're either consumed or observed on the other side. So in an actor model, I consume the message and I do my work and nobody else does. In an observation model, it's pub/sub. I'm publishing it to everybody. This gives us a really nice structure to put on the messages. And we'll use this structure to look at various failure modes. You can see from this talk and the other talks yesterday that we're in a kind of search phase in microservices. We're trying to come up with design patterns. We're trying to come up with structures that let us conceptualize them. Because ultimately, a year from now and 2 years from now, when the microservices are out of the trough of disillusionment, we still have to do that piece, CIOs and CTOs are going to be asking you as architects to build these systems. And if you're building them by just arbitrarily trying to figure out, oh, what services should I build, you don't have a conceptual structure to design your system. And all of this work that a lot of us are doing is about trying to figure out what's the best way to design and conceptualize these systems. So this particular approach and the message approach, one of the ways that we use it, and again, this is a field report, one of the ways we use it with our clients when we're building systems is it lets us define service specifications only in terms of messages in and messages out. So that's really nice because the team lead or the architect can do a little bit of analysis, define services in terms of messages, and then farm out the work. And your team can operate in parallel. Some of the conversations around coffee yesterday, the discussion was, we need to update our microservice with a new feature, but this other microservice, their API wasn't implemented. And then, well, we had to wait for them, or we had to have some complicated mocking system or something like that. That's a real problem if you don't have a structure underneath you that deals with that. But if you use messages, if you abstract the transports, it's really easy to mock up messages. You don't have to wait for the other guys. You can just mock the messages. And it isn't something that you have to do as a special case. It's just inherent in the system. So if we look at some of the specifications for some of these services, they're pretty simple. And these actually correspond to some of the specifications that we actually use in practice with junior developers. So the web microservice at the front end, there's no messages coming in apart from HTTP requests, but I'll take a slight diversion here. The outside world is different from the inside microservice world. You should never have a situation where outside requests end up being served by internal microservices. That's a real security nightmare. There is an API gateway, a hard boundary around the system. You expose a traditional REST API because that's what everybody needs to integrate. But the inside of your system, the messages are in a different universe. They're a different kind of message altogether. The messages I'm talking about here are internal ones. The web microservice sends out 2 messages, the command search one and the role info command get one. You've seen those already in the diagrams. And the developer implementing the service can use the specification to know what they're supposed to do. The search service accepts the role search command search message because it's going to go and talk to Elasticsearch. It also accepts an insert message. So when the update service gets a new update, it'll trigger this insert message. I need to get data into my search engine somehow. If you look at the info service and you look at its interactions with the NPM service, this is where you have this 200 millisecond timeout effectively. Role info request part is the outbound message, and then role info response part is the inbound message. These patterns and these names are utterly arbitrary. You can invent your own. It doesn't really matter, right? These are the things that just came into my head because that's the way my head works. You could call them whatever you like. The important thing is these are not message types. These are patterns matched against the content of the message. This is why, even if you're using a message bus, the problem is that the topics are essentially message types. And message types are ultimately, if you sort of take a hard line with this, are ultimately addresses. They're ultimately no different from IP addresses and ports on the network. Ultimately, it's knowledge that one microservice has of another, and that's what we're trying to avoid. A microservice thinks it lives in a universe where there is nothing else, only messages. Analogous to the service specifications, you also can define how the system fits together. How do the messages wire up? So if I kind of invert the view, and I can say, from the perspective of each message, what are the service interactions? So role search command search is a consumed message from web to search. And the same for role info command get. And for example, when the update service gets an update from NPM, it generates a change message, which is under a pub sub model. It's only observed. So I can, as an architect, write down these interactions. And here's the interactions for the info page where it sends out a message and then waits for messages to come back. So between the service definitions at the service level and the message interactions at the system level, you can have a very, very nice way to define, from a business logic perspective, the system itself. And you don't have to define it in terms of network diagrams or topology or implementation or any of that sort of stuff. So Chris Richardson has now legitimized the approach of developing microservice chassis, he calls them, which essentially lets me say, hey, we have a framework that does this stuff. Now, the ideas are more important than any implementation. You can do pattern matching in Scala, you can do pattern matching in PHP, it doesn't really matter. But in order to show you some code, obviously I'm going to need some sort of framework and base to make this work. This is the framework that we use for Node.js that we've built over, we started in 2010 actually, before it was even network capable. And there we go. One of the nice things about having a system like this is you're embedding a little utility library inside each microservice. And that utility library lets you do things like implement throttling and circuit breakers and tracing and all that stuff that gives you fault tolerance. You kind of get it for free. So again, if you're doing a direct HTTP call inside your microservice, you have to implement all that stuff yourself. Or you have to have intelligent load balancers that do it for you. But if you do it as a little library, it makes your life a lot easier. So I'm going to show you a little bit of code. I'm going to show you this system kind of running, and then we might stop and start a few services and look at a few failure modes. There we go. Okay, so this is the list of running services. It gets really painful if you're building microservice systems to run them all from the command line. So this is a little tool called Fuge that we've written, which kind of controls all the different services. And you can see in this system, you can see that there's the services we've been talking about, the web service and the search and the info and all that sort of stuff. And the way that they fit together is, here's my search engine, and if I type in, I don't know, G or E, you can see I'm generating results. So this is going through the full end-to-end, talking to Elasticsearch. All of this stuff, by the way, is kind of a workshop that I do at conferences as well. So you can step through the whole application step by step and build it up over time, piece by piece. The info page that I've been talking about looks like this. So this is going to go out and get data about this gex module from NPM and from GitHub, unless I've already got the information and stored it in a local database. So one of the ways that one of the things that your microservice system is supposed to do is make it easy to understand what's going on. And there's a couple of ways that you can do that. So last year when I was here, I was talking about measuring message flow rates. That's a really, really useful and interesting way to see how your system works. So I'm going to show you that as well. And I should have that already set up. So again, this is just some tooling to show you. This is capturing flow rates through the system. So if I go and do some searches, you can see that the dashboard is showing me activity. And you can see that this is capturing messages per second for all the different services, looking at it from the perspective of individual messages, and then looking at it from the perspective of individual services, and capturing their memory usage and all that sort of stuff. So the thing about microservices is they're meant to be able to scale. So one of the ways of dealing with faults, and where a fault might be too much load, is you can run more than one service. So if I look at my search service at the moment, you can see that there's only one instance of that search service. So maybe I want to scale up by running multiple instances. So I only have one running at the moment, but I can say start search. And that's going to fire up. I have two instances of that running now. And if I do another search, you can see that you can see I have two instances here, this one and that one as well. The message flow rate for searches stays the same. Now, that only works if you're using an intelligent load balancer or if you're using a message bus, because my system still has to know that now there are two search services available. And one of the things that will be the subject of a future talk, but I haven't had time to do any prep for it yet, is more advanced techniques for service discovery. So there have been talks about service discovery at this conference, and there are fairly well-established techniques where you use something like console, or you do DNS, use Zookeeper, use load balancers. There's all sorts of different techniques or topics on a message bus. But one of the more recent techniques that we've seen used comes from Uber, where they're using something called the SWIM algorithm. And I've forgotten what it stands for exactly, but the basic idea is that instead of each microservice, when it starts up broadcasting to the rest of the network, which might be hundreds or thousands of microservices, it uses an infection protocol to let the rest of the network know. So it only tells a certain subset of microservices, and then they then propagate the information. The nice thing about that is it's zero configuration. So I don't need to know the IP and address, IP and port of another microservice. And if you look at it at the code level, it's really nice because you get to do this sort of stuff. So if I look at Nodezoo web. So this is the sum total of the configuration I have to do. I say join this mesh network. I don't have to know about any other services, what they're doing, or anything like that. In fact, the nice thing is I don't have any order dependency on startup. I can start up this service, the web service, or the search service in any order, and they'll share information about which messages they can handle dynamically. And if I look at the search side, you can see that I'm using the same line of code, join the mesh network, and I'm saying, I know how to handle role search messages. And that information, along with my address and port number, is propagated to the rest of the network. And when I started that second search service, that information was propagated again. And if I kill one of the search services, the fact that I'm dead will be noticed by my peers really, really quickly. So I don't have a heartbeat. I just have my peers checking randomly, which means it's much faster. The fact that one of the search services is dead will propagate through the network, and the little client-side load balancer on the web service is going to take it away. So things keep working really, really fast, really nicely. If you look at that logging output, it's a little bit detailed, right? So you can see what's going on, but you can see that when I fired up a new search service, ultimately, this logging is an indication that all the other services got to know about it. So that is one way that you can deal with failure, because if you make the system autonomous and you don't have single points of failure like a service registry, you can handle many other types of cases. One of the other important things that a framework gives you is things like correlation IDs. So you need to be able to trace activity through the system. A microservice starts a request, and then it may bounce across a couple of different microservices. So in our case, if we look at searches, I go back and just do a simple search. Here's the activity that was generated by the search. So this is my correlation ID. And you can see the 5Q. So I've made them really small, right? In production, they'd be slightly larger. You can see the 5Q is propagated over the different services. So I know that this was one particular transaction, for want of a better word. But you can also see that this ID is then traced over the web service to the search one, and I can follow the path exactly. And we're developing tooling around this to chart this up nicely, so you can kind of see these interactions. That's why I say, we're still heading for the trough of disillusion, because the tooling to make this easy isn't there yet. You still have to troll through log files to understand this type of stuff, or write custom systems to understand it. Okay. So. Okay, so like I said, all of that code is working code. You can go to the GitHub repo and download it and try it out and get it up and running. It's structured as a series of iterations, so it's meant to give you a feel for, okay, I'm going to do microservices first, not a monolith. What does that actually look like in practice? And each branch is an iteration representing a week of work. So in the first week, you only do a very simple, very general solution, and then each week you start adding more microservices that specialize, and you start adding more features. And it's just to give you a flavor for what that actually looks like in a wider context. So let's return to our structure. We have this classification for messages. And now we can ask the question, okay, so we have these different types of messages. How do they fail? Well, the first one is the synchronous request response. And the first failure that we look at is perhaps the most classical one, which is solved by the circuit breaker pattern. You have a slow downstream. This is the worst case scenario. So if B that you depend on has failed completely, that's actually a much easier scenario, because you start you'll detect that it's gone, for example. But if B is just getting slower and slower because it's running out of disk space or something like that, your whole system starts slowing down. The circuit breaker pattern is really a decision to be hard line about this. Collect stats about the downstream services that you rely on, and if they start becoming too slow, consider them dead. Even if they aren't officially dead, consider them dead. And generate alerts or whatever. Of course, you might have a whole bunch of messages piling up in A. You've got to be hardline there too. So if messages become too old, just drop them on the floor as well. The whole idea here is you're assuming that there are going to be scenarios where it doesn't matter how much auto-scaling you have and how much you've thought about the problem, you're not going to be able to handle the load scenario. Denial of service attacks, for example. Or even a badly written internal service, which generates tons of traffic, because it's going to happen. If you look at another failure mode, so these failure modes, the way that I've structured the message classifications, all the messages are subject to all of the failure modes, but in our experience, these are the ones that dominate. So these are the ones that dominate synchronous request response. Upstream overload is sort of the reverse of the prior one. And this is where you're sending messages to somebody else and you're too fast for them. Presumably, B is doing more work, is more CPU intensive or whatever. So A might be taking in image URLs and B might be resizing the images. You need to use back pressure. You need to use some sort of back pressure mechanism so that B can say to A, I can't handle this workload. If A just keeps on piling on work, eventually your system collapses. The synchronous but observed pattern is kind of a weird one. So when you create a structure for classifying or analyzing things, and you kind of create categories, often you discover new patterns that you weren't using. So typically in microservice systems, you see synchronous request response, and you might see asynchronous fire and forget. But there are actually other patterns. So this particular one is one where you have a primary microservice that's doing the work, but you might have an observer, like an auditing service, that's capturing events. Or I was speaking to somebody yesterday who was asking, how do you do reporting in microservices, especially if you don't have a common database? Well, one way you might do that is you might have the reporting system might be capturing events as they flow through the system. You're using event sourcing, for example. The failure modes that happen here are things like lost actions. So you have this A to B interaction, but suddenly C doesn't seem to be seeing, maybe C has run out of memory or crashed or something like that. The way that you know that something's going wrong is you check the message flow rates. So that's why I was showing you those charts, because if I have a set of business rules that I've mapped to messages that are implemented with a set of services, I can be pretty sure that I expect to see certain flow rates. And if those flow rates change, I know that something's going wrong. This is a favorite one of mine. So there's a natural tendency among programmers to try and tie the world down, try and be hyper-specific. And it really seems to be a deep longing for exactness. But in a microservice world, it's exactly the wrong intuition. Because if you define strict message schemas, because you're trying to be correct, you actually end up losing a lot of the advantages. If you have a strict schema and you update only some of your microservices, you break other ones. In fact, you don't have a microservice. This is back to distributed monoliths again. Obey Postel's law, right? John Postel was the guy who invented TCP/IP. He knows what he's talking about. Be liberal in what you accept, strict in what you omit. It means that you can update your whole system with a single unit of deployment. Microservice systems should only be changed one service instance at a time. And there may be versioning conflicts, so you need to be able to handle different versions of different messages. The winner-take-all pattern is subject to some well-known message bus failure modes. Poison message is a classic one. There's a message in your system, the data within it triggers a bug in the receivers and causes them to crash and stays on the queue. And the next service reboots and takes it and it crashes. And eventually all of your services are crashing and the queue is stuck. This is where a framework comes in really handy because it can keep track of recently seen messages. If it keeps seeing the same message again, it knows something's horribly wrong and it can just drop it on the floor. This, again, goes right back to this Kintsugi principle. You have to assume that there's going to be failure. You have to not be afraid to throw messages away. You can't get 100% correctness. Another one that people often ask for is, well, I need to guarantee certain things. So I want to get guaranteed delivery of messages, right? At most once, or exactly once, or whatever. This actually isn't possible. So who's heard of the Byzantine generals problem? Anybody? Okay, this is a fun one. Okay, so you're a general of the Byzantine emperor, and you're attacking a barbarian city, and the barbarian city has 10,000 soldiers. So you have an army of 6,000 soldiers at the top of one hill, and at another hill on the other side, you have another army of 6,000 soldiers. So that's 12,000 versus 10,000. You're going to win. The problem is you have to get a message from the top of this hill to the top of that hill. And you don't have mobile phones or anything. You have to send some poor soldier running down the valley, past the city, and up the other side of the hill. The barbarians in the city know this, so they're going to be looking out for your messengers. Some of the time, they're going to capture them and kill them. So if you send a message to the other general on the other side of the city saying, attack at dawn, that messenger may not get through. Now, if he doesn't get through, you hear nothing back, so what do? Do you attack at dawn? If the messenger does get through to the other general, that general says, great, okay, I'll send a message back to confirm. Same problem. He doesn't know unless you send yet another acknowledgement. It's actually logically impossible to be absolutely 100% certain that the messages are going to get through. So if you're looking for certainty in a distributed system, you won't find it. It just isn't possible to actually implement. But you can protect yourself against these types of failure modes by using things like idempotency. So if you see the same message being repeated, you just assume it's some sort of error, or you design your system so that it doesn't cause a problem. If I'm resizing images, I'll just resize the image again. It's a bit of wasted CPU, but who cares? Finally, the fire and forget mode. And this is the fun stuff, right? This is where microservices bite you in the ass, because you're flying along and you're building the system and you're delivering features, and it's all fantastic and wonderful. And then you get emergent behavior. It's actually surprisingly easy to end up with a loop in your system. If you end up with tens or hundreds of services, you can easily end up with this situation, especially if your architect isn't paying attention. This is where the correlation IDs come in handy, because you can actually understand and trace what's going on. You can see, hey, this is a message that I sent out originally. This is a loop, so kill it. Even worse than the emergent behavior is catastrophic collapse. And this is where you add a single instance of a new microservice, and whatever you've done, you trigger a feedback loop that grows exponentially. So as messages come in, it starts sending out more and more other messages. Rolling back the system. So in this case, where you get emergent behavior, often the solution is just roll back that individual microservice and you're back to a known good state. In catastrophic collapse, you can't do that. You might roll back the microservice or turn it off, but your system is still going crazy. Your options there are to have a kill switch. So the ability to selectively shut down large sections of your system to essentially introduce a fire break is an important part of a production microservice environment. And again, using frameworks makes it easy, because you can, in whatever library you're using inside each individual microservice, you can implement kill switches. A lot of this stuff is inspired by a really old book. So this book is called Normal Accidents. It was written in 1984 by a guy called, a sociologist called Charles Perrow. And he analyzed why nuclear accidents like 3 Mile Island happened. And the whole point of the book, and there's a German translation actually, the whole point of the book is once you build sufficiently interesting systems, and in Fred George's language, once you build systems that are complex or chaotic, there will be normal accidents. The systems will fail no matter how much engineering you apply, there will be failure. It's simply a feature of these systems. So how do we, as software developers, or if we like to call ourselves software engineers, how do we deal with this fact when the business people are asking for perfection? And I think the important thing is you have to change the discussion. You have to have the ethical backbone to present the system and what you're building in the right way. So instead of accepting the challenge of building a perfect system that has no failures, present the system in a different way. Ask where the business trade-offs are. What is an acceptable failure rate? Have that discussion with the business stakeholders. Because you'll often find that failure rates are acceptable. Business people their job is to make decisions about risks and rewards. You just have to put it in the right context. There are, for example, when you go to a supermarket and you buy things, the barcode scanner has an error rate, not just in the physical laser, but also in people inputting prices. And in fact, the American Supermarket Association requires that prices at a till are no more than 98% accurate. So on the business side, you can see that failure is acceptable. We sort of have this hubris because we're logical and we think we're engineers that we have to build perfect systems and we come up with ACID transactions and things like that. It isn't necessary. A lot of the reasons that teams end up on death marches and working at the weekend is because they're trying to build systems that are too perfect. Find out where the real business trade-offs are, find out what the acceptable failure levels are, and that makes microservice systems work because they have embedded continuous failure. This problem has already been solved. It's been solved by evolution. If you look at cells in your body and the cellular life cycle, it goes through a number of stages. Mitosis is where cells separate, and that's scaling by growth. Apoptosis is really interesting. That's where cells have programmed death. The cell dies under certain conditions. So, the analogy there is don't have long-running microservices, kill them after a couple of hours and keep recycling. Senescence is what happens to cells when the telomeres at the end of the DNA reach zero. The cell enters a state where it neither divides nor dies. And in fact, recent research shows that most of the effects of old age come about because you have these senescent cells that won't go away. And if you have long-running systems, you're just going to expose yourself to failure modes like running out of memory. So die to stay alive. I think the philosophical stance that microservices enable is much, much healthier than monoliths. Because you're dealing with reality, the reality that things are going to fail, but you're still going to have business success. Thank you very much.
Thank you.